Because instead of considering a rectangle of size 2 by 3, you can even consider a rectangle of size 3 by 2 like this. Once you've selected the numbers, so the arrangement is done automatically. So because the smallest number will be taken as the value of I, the next number is j, etc. So that means only selection is our job, right? The arrangement is done automatically. So these 5 balls are not going to be arranged. Overall there is an arrangement. So these 5 balls here or here, it matters. But within the box, the balls are not to be arranged, right? But 10 factorial x1 can be 0. If x1 is 0, he has visited the place on the first day itself. Similarly, x5 can be 0. So that means he has visited on the when you consider this rearrangement of the remaining 5 objects, so here the letter 2 corresponds to the envelope 1. But we have considered the cases in which the letter 2 is not placed in envelope 1. Hi Pinto. I thought of doing some questions based on the concepts of permutation and combination. Are you game?
Yes, I am.
So here is the first question. The number of ways to place a white rook and a black knight on a chessboard such that neither one can capture the other is. Alright, so here in this question, a chess game is given with just two pieces, a rook and a knight. The rook, it will always move in a straight line path either in the horizontal direction or in the vertical direction, and the knight moves in an L shape, 2 steps in one direction and 1 step in the perpendicular direction. These two pieces are placed on a chessboard in such a way that neither can capture the other. In how many ways can this be done? So that's what we're going to find out. Alright, so let us first consider the cases in which the rook captures the knight. Alright, so that is the first case, rook capturing the knight. So the rook can capture the knight when both these pieces are placed on the same line. Alright, so let us select one of these horizontal lines, right? So each horizontal line is called a row, right? Let us select a row. So one row can be selected in 8 ways because there are 8 horizontal lines. A row can be selected in 8 ways. Alright, one row is selected. On this selected row, we will place both these pieces. Alright, in how many ways can this rook be placed? So let us first place this rook. So each row contains 8 squares. So one of the squares can be selected in 8 ways. So rook can be placed in 8 ways. Now the knight can be placed in one of the remaining 7 squares. So the knight can be placed in 7 ways. Alright, this product will give you the answer. But this value is multiplied by 2. So why do we multiply by 2? So instead of horizontal lines, you can even select vertical lines. There are similar 8 vertical lines. So same number of arrangements we will have for the vertical arrangements also. So you multiply this by 2. So this is for the column, means the vertical line. So this is the total number of ways in which a rook can capture the knight. Alright, done. Alright, similarly we will consider the next case, a knight capturing the rook. So in how many ways can we place them so that the knight captures the rook? So let us consider this rectangle of size 2 by 3, right? 2 rows and 3 columns. On this rectangle, we will place both these pieces on 2 opposite corners. Then the rook will capture the knight. I mean the other way around. The knight will capture the rook, right? So that means we will first consider one rectangle of size 2 by 3, and then we will place these 2 pieces on these 2 corners. Alright, first let us see how many such rectangles are there on the entire chessboard. Alright, so first find how many such rectangles are there in the first row itself. Alright, 1, 2, 3, 4, 5, 6. So 6 such rectangles are there in the first row alone. Now similarly, how many such rectangles are there in the first column? Alright, so 1, 2, 3, 4, 5, 6, 7. So 7 rectangles are there in the first column. So totally how many such rectangles are there? So that is 6 multiplied by 7. So this is a rectangle of size 2 by 3. Alright, 2 rows and 3 columns. So 6 times 7, 42 such rectangles are there in the entire chessboard. Now we have selected one such rectangle, for example the first one. Now we'll have to place these 2 pieces. Alright, first let us place this knight. So the knight can be placed in any one of the 4 corners. So it has 4 choices. And now we will place the rook only on the opposite corner. So it has only one choice. So the rook can be placed in only one way. So this value we will multiply by 2 again. Because instead of considering a rectangle of size 2 by 3, you can even consider a rectangle of size 3 by 2 like this. So similar number of cases, so 2. So this is a rectangle of size 3 by 2. So this is the total number of ways in which a knight can capture the rook. Alright, but that is not the question. We'll have to find the number of cases in which these 2 things cannot happen. Alright, so what we do is, from the total, our required answer is, from the total is what? totally, in how many ways can the rook be placed? 64 ways. There are 64 squares. So in one of the squares the rook can be placed. So 64 ways we can place the rook, and in remaining 63 squares we can place the knight. So randomly these two pieces can be placed in 64 multiplied by 63 ways. From this we subtract these two cases, we'll get our required answer. Alright, minus, so this value I'm writing as it is. So 8, 8, 7, 2 minus, so this value 6, 7, 4, okay, 2. Alright, so let us take out the common factors. So 8 times 7. Alright, this can be taken out. So then 8 multiplied by 9. So that is 72 minus 8 times 7. So 16 minus, again 8 times 7 taken out. So minus 6. Alright, this gives you the value. So 56 multiplied by 72 minus 22. So that is 50. So this gives you the answer 2800. So this 2800, so that is the number of ways we can place these two pieces on the chessboard in such a way that both of them survive. The number of ordered triplets A, B, C of subsets of a set B containing n elements satisfying the conditions n of A intersection B equals 2, B intersection C equals A intersection C equals null set, and n of A union B union C complement equals 3 is. Alright, so here in this question we are given a set with n elements having subsets A, B and C satisfying certain conditions. Using that we need to find the number of possible combinations of these subsets. Alright, so here the subsets A and B have 2 elements in common, B and C have no elements in common, and A and C have no elements in common either, and outside this A union B union C we have 3 elements. With all these conditions, let's find the number of possible ways to form the sets A, B and C. Alright, so we'll do this question by 2 methods. So the first method may be a little lengthy, but anyway, what's wrong in learning a method? So we'll do by both the methods. So here the intersection of A and B have 2 elements in common. So which 2 elements? Any 2 among the n elements of the set. So let us first select 2 elements from the total elements. So A intersection B have 2 elements. Alright, so let us select these 2 elements from the total n elements. So n C 2 ways this can be done. So we have selected 2 elements. Alright, now the outside A union B union C we have 3 elements. So that is A union B union C complement. So that has 3 elements. So let us select 3 elements from the set. 2 elements are already selected for the intersection. So from the remaining n minus 2 elements, so we have to select 3 elements. So totally we have selected 5 elements. Then remaining, so remaining we have n minus 5 elements. Alright, so how to deal with this n minus 5 elements? So that's what this question is about. Alright, so let's form the sets A, B and C using the remaining n minus 5 elements only. Alright, so let us take cases. So A and B. So depending upon how many elements are in A, so we'll divide it into many types. Okay, so the number of ways. So number of ways to form the set A and the number of ways to form the set B. Alright.
What about set C? You are not considering that.
See, we don't need to select the set C, because once we select some elements for the set A and B, the remaining elements will automatically go to the set C only, because there are no other options. Alright, so we fix elements for the set A and B. So C is not to be considered because that is automatically set. Alright, so n of A, the minimum value is 0. So this is apart from the elements in the intersection. Though I denote this by n of A only, so this 0 is the number of elements apart from the intersection. So A already has 2 elements minimum. So this is apart from those 2 elements. So A has no more elements. So A has 0 elements. So how many ways can this be selected? So n minus 5 C0. From the n minus 5 remaining elements, you select 0 element, which means just one way. So A has 0 elements. Then B should have no intersection with A, because already the intersection has only 2 elements. Apart from that, no more intersections. So B should have no intersection with A. But A already has 0 elements. So whatever is the set B, so it will have no intersection with A, right? So that means from the remaining n minus 5 elements, you can form any subset. So that is 2 to the power n minus 5. So that is the formula for the number of subsets, right? So n minus 5 elements are there. We can form subsets in 2 to the power n minus 5 ways. So that is done first case. Alright. Similarly, so the next one, n of A is 1. So A has just one element. So how many ways can this be selected? So n minus 5 C1. Okay, so one element is selected. Now B cannot have the same element. Alright, so apart from this one element, B can have any subset from the remaining n minus 6 elements. So which means, so 2 to the power n minus 6. So it will go on like this. Okay, so finally, suppose A has all the n elements. That means it can be selected n minus 5 elements. Totally n minus 5 only we are left with. So n minus 5 from this n minus 5 we can select all n minus 5. That means this is 2 to the power 0. So no element is left for B. Now to calculate all these possibilities, we have to multiply these values and add all these cases. So let us do the multiplication here. So n minus 5 C0 multiplied by 2 to the power n minus 5 plus n minus 5 C1 2 to the power n minus 6, etc. Alright. Similarly the last term. Now if you add all these values, if you observe, so this is the expansion of the binomial terms, right? So n minus 5 C0 2 to the power n minus 5. So this is the expansion of 2 plus 1 to the power n minus 5. Is that okay? So this is the expansion. So n minus 5 C0 2 to the power n minus 5. Next n minus 5 C1 2 to the power n minus 6. So this is the expansion of 2 plus 1 to the power n minus 5, which means 3 to the power n minus 5. So this is the number of ways we can distribute the remaining n minus 5 elements. But already we have different cases here. So our required answer is, so multiplication of all this. So nc2 is the number of ways to select 2 elements initially, and the next 3 elements, so n minus 2c3. And the remaining n minus 5 elements can be distributed in 3 to the power n minus 5 ways. So this is the number of ways. Now if you do the simplification, so this will be equal to n factorial divided by, so n minus 2 factorial multiplied by n minus 2 factorial divided by n minus 5 factorial 3 to the power n minus 5. Okay, so that can be further simplified. So this n minus 2 can be cancelled. Alright, and this n factorial by n minus 5 factorial, so that can be written as np5, isn't it? N factorial by n minus 5 factorial, that is np5, and 2 factorial, so 1 3 can be cancelled here, so 2 times 2, that is 1 by 4, and multiplied by, so 1 3 can be cancelled here, so 3 to the power n minus 6. Okay, so that's all. So that is the answer to the question. Alright, so this is one of the methods of solving this question. Right, so now we'll do by another method, right? So alternative method. Now here you see, so it's the same thing. So first we will have to select 2 elements, so that is same. So we'll have to select 2 elements, so nc2. Okay, done. From the remaining n minus 2 elements, you have to select 3 elements. So that is same. Alright, now we are left with the n minus 5 elements. In how many ways can you distribute this n minus 5 elements? So very simple. See, we have divided the whole part into many regions. Alright, but that the intersection part is already filled with 2 elements, so we are not going to put any more elements in that intersection, and the outside part also has 3 elements, no more elements. So now we are left with just 3 regions. The part that contains only A and only B and only C. These are the only 3 regions available for the remaining n minus 5 elements. So let us take one of these elements. So that can have any one of the 3 regions, right? So 3 possibilities. So that element can be put in any one of the 3 regions. So that has 3 possibilities. So 3 ways we can put that element. Alright. Similarly, the next element, again that has 3 possibilities, either in A or B or in C. So 3 possibilities. That means totally 3 to the power n minus 5. So that's also, that is the answer. So this is another way to do this question.
The second method is very simple. What's the use of the tedious first method?
See, you don't make a choice while learning a method, okay? So while solving a question, we can choose a method that is appropriate for that particular question, because not all the methods work for all the situations. So learn all the methods and use as and when required. Alright, so for example, this question. The number of ordered pairs A, B of subsets of a set containing n elements satisfying the condition 1 less than or equal to n of A less than n of B is. Alright, so this question is similar to the last question. Here too we need to find the number of possible combinations of the subsets A and B satisfying certain conditions. Here it is given that n of A is less than n of B. So this question can also be done by 2 methods. So the first method is similar to the last question, like so 2 subsets are given A and B. Now based on the number of elements in the set A, so we will divide it into many cases, right? So the number of ways to form the set A, and similarly the number of ways to form the set B. Alright, so what is the minimum value of n of A? 1. It's given that n of A is greater than or equal to 1. So let us take the first case. A has only 1 element. This 1 element can be selected in nc1 ways. So this is the number of ways to form a 1 element subset. So nc1 ways. Now n of B is more than n of A. That means B should have minimum 2 elements. So let us select a 2 element subset. So nc2, or it can have 3 elements. So nc3, or it can have 4, 5, or it can have all n elements. So this is the number of ways to form the set B when A has just 1 element. Now similarly, let us take the next case. A has 2 elements. So these 2 elements can be selected in nc2 ways. So then B should have minimum 3 elements, so NC3 or NC4, etc. up to NCn. Now, so we can continue like this. So the last case, A has n minus 1 elements. Alright, so this can be selected in NCn minus 1. Now, then B should have NCn, all n elements. Alright, so these are the various cases. Now, to calculate the total, just like the last question, we have to multiply these two values and then add all these cases. So that will give you the value. So NC1 multiplied by NC2 plus NC3, etc. up to NCn, plus the second term NC2 multiplied by NC3, etc. up to NCn, plus etc. Many more terms are there, so we'll have to multiply all this, and then finally this total is to be calculated. Now if you observe this, this is the sum of the product of binomial coefficients taken two at a time, right? Like NC1 multiplied by NC2, NC1, NC3, NC2, NC3, all combinations of binomial coefficients, and this is what we denote by the symbol, right? So the double summation. Alright, double summation NCi, NCj, where I is less than j, less than equal to n, greater than equal to 1. So what essentially we need to find is the double summation. We know how to find this value, right? Alright, this can also be denoted by the symbol S2. So this is another way to do this question. So let us denote this by the symbol S2. S2 is what? Sum of values multiplied, taken two at a time, and finally the sum is added. Alright, so this is S2. So which formula has S2? So it is like this. See, take this formula A1 plus A2 plus A3 square, so that equals A1 square plus A2 square plus A3 square plus 2 times A1 A2 plus A2 A3 plus A1 A3. So this is A1 plus A2 plus A3, so that can be denoted by this summation, right? Summation AI square. So that equals, this is sum of squares of values, summation AI square plus 2 multiplied by, this is A1 A2 plus A2 A3 plus A1 A3. So this is the sum of product of values taken two at a time, and that is what we denote by the symbol S2. Alright, so that S2 is what we need to find here. So let us find S2 from this formula. This is S2 equals summation AI squared minus, or let's say A squared divided by 2. So let us use this formula to find the value of S2 here. So here in this example, so this summation AI here is the sum of all binomial coefficients, right? Like this one, summation NCi squared minus summation NCi squared divided by 2. Is that okay? So these two formulae are known to us, right? Summation of NCi, what is that? Sum of all binomial coefficients. So that is equal to, so 2 to the power n minus 1. Right, because so it doesn't start from 0, it starts from 1, because I starts from 1 to n, right? So not 0. Alright, so minimum value of I is 1. So here also I is from 1 to n. So we subtract that first term NC0. Alright, so this squared minus, this is summation NCi squared. So that is also a formula 2NCn, again minus 1 because NC0 is not there. So this is the formula for the sum of squares of binomial coefficients, right? So this thing divided by 2. So if you simplify this further, so this is 2 to the power 2n minus 2 times 2 to the power n plus 1. So here also plus 1. So plus 2 minus 2n cn. So this value divided by 2. So if you divide this by 2, you'll get 2 to the power 2n minus 1 minus 2 to the power n plus 1 minus. So this can be simplified. So 2n cn can be written as 2n divided by n multiplied by 2n minus 1 cn minus 1. Alright, so let us use that formula so that we can cancel this 2. So this will give you 2n minus 1 cn minus 1. So that's it. So that is the answer to the question. Alright, now we'll also do this question by another method. Alright, alternative. See, first let us find the total number of combinations of subsets A and B, okay, without any condition. See, total. See, A is a subset of the given set, so that can be selected in 2 to the power n ways, right? That is the formula for the number of subsets of the given set. But here, we'll also subtract this 1 here, as n of A is minimum 1. A cannot be null set, so that case is removed. Now, similarly, B can also be selected in same number of ways, so this square. Alright, this is the total number of ways to select the subsets A and B. Now, from this, we subtract the cases in which A and B have equal number of elements. So remove all the cases in which A and B have equal number of elements. See, for example, A has one element, so NC1, and B also has one element, so NC1, NC1. Similarly, two elements, so A has two elements, B has two elements, etc. All n elements. So this is the number of ways to form two subsets having equal number of elements. So that case is removed. That means what is this total? So this total will give you the number of combinations of subsets which have different number of elements. Either A is a bigger set or B is a bigger set. But here in this question, we need to find all the cases in which A is a smaller set compared to B, which means half of these cases will be our required answer. So this you divide by 2. Because in half of the cases A will be the bigger set, the remaining half B will be the bigger set. So you divide this by 2. So that is our required answer. Alright, so let's simplify this. This is 2 to the power n minus 1 squared minus. This is again nc1 squared plus nc2 squared up to ncn squared, sum of squares of binomial coefficients. So that the same formula here. So 2ncn again minus 1, so divided by 2. So this is the same expression we got here. So if you simplify further, you will get the same answer. Alright, so this is also another way to do this question. Let S be the set 1, 2, 3, 4. The number of unordered pairs of disjoint subsets of S is equal to. See, this question is similar to the other questions but very simple. So there are two subsets given for the set and also they are disjoint. So we need to find the total number of possible combinations. So let's take the given set to be this one containing elements 1, 2, 3 and 4. Alright, which means the rectangle contains all the elements 1, 2, 3 and 4. But there are two subsets given for the set, say A and B, which are disjoint. Alright, so now each element has now 3 choices, right? Because it can be either placed here or here or here. So 1 has 3 choices. Similarly, this element 2 has 3 choices. Similarly, 3 and 4. So each element has 3 choices. So 3 to the power 4. This is the total number of combinations of subsets of the given set. But that is not the answer. It is given that these two are unordered subsets. What are unordered subsets? So take this example. So take this example. A has 1 and 2. B has 3 and 4. Take another example. A has 3 and 4. B has 1 and 2. Are they different or same? See, if they are ordered subsets, they have a name A. So that means 1 and 2 are in A, the first case. In the next case, 3 and 4 are in A. Obviously, they are different. But if they are unordered subsets, so there is no labeling, right? So one set has 1 and 2, the other set has 3 and 4. So both the cases are considered same. So that means this is a repetition. So this is not our answer because it has a lot of repetitions. So half of them will be repetitions, right? Because so anything, if you interchange, that will be another possible combination, but that should not be counted here. So the total 3 to the power 4, so we make it into half. But there is one combination which will not repeat. So that appears only once. So that is this combination. So null set, null set. So these two sets, the null set, null set. So this, even if you interchange, you will get the same value. So except this combination, all other combination will appear 2 times. So that means you subtract this one particular case and make it into half. Alright, because except this, all other combination appear 2 times, so we make it into half. And finally add this case also. That's all. So let's do the calculation here. So this is 80 by 241. So 41 is the total number of unordered combinations of subsets of the given set A and B. Alright, so that is the answer to the question. Four sets S1, S2, S3 and S4 are given below. If the total number of elements in the set SR is NR for R equal to 1, 2, 3, 4, then which of the following statements are true? Alright, so this question appeared in the exam very recently and it's a very simple question. So we are given 4 sets S1, S2, S3 and S4. We need to find the number of ways to form these 4 sets. Alright, so let us do it one by one. See, N1 here is the number of ways to form the first set S1. So what is S1? S1 contains all these ordered triplets of values I, j, k, which can take values from 1 to 10. So in how many ways can you select values for I? I can be selected in 10 ways. Alright, so any one of the 10 values, 1, 2, 3 up to 10. Similarly, j can be selected in 10 ways, k can be selected in 10 ways. So that means, so this is the answer. So 1000, that is the value of N1. So the number of ways to form the first set S1. Alright, similarly N2. So the number of ways to form the set S2. Now this has some restrictions. 1 less than equal to I, that is less than j plus 2 less than equal to 10. So this means j plus 2 is less than equal to 10. So that means so j is less than equal to 8. So the maximum value of j is 8. So let us consider all the cases. So j and I. So j can be 8. The maximum value of j I am taking. So when j is 8, I is less than 8 plus 2, 10. So I is less than 10. So what are the possible values of I? 1, 2, 3 up to 9. So that means there are 9 possibilities here. Alright. So let's take the next case. So j is 7. So when j is 7, I is less than 9. So I is less than 9. So it can take values 1, 2, 3 up to 8. So this has 8 possibilities. So we can continue this. So I'm directly writing the last case. So the least value of j is 1. So I is less than 1 plus 2, 3. So I is less than 3. So it can take values 1 and 2. So this has 2 cases. So if you add all this, alright, we get 9 plus 8 plus 7 plus 6 up to 2. So that is 45 minus 1, right? 44. So 44 is the value of n2. So that is the number of ways to form the set S2. Similarly, let's find n3, which is the number of ways to form the set S3. So S3 contains a combination of 4 letters, right? I, J, K, L. So that means among the 10 numbers, we need to select 4 numbers first. So let us select 4 numbers. So 10C4. We've selected 4 numbers from the 10 numbers 1, 2, 3, 10. Alright. Now we have to arrange them. So how many ways can you arrange them? There's only one way we can arrange, right? Because the arrangement is automatically done. So it is given that I is less than J, less than K, less than L. So that means no arrangement. Once you've selected the numbers, so the arrangement is done automatically. So because the smallest number will be taken as the value of I, the next number is J, etc. So that means only selection is our job, right? The arrangement is done automatically. So this is the value of n3. Alright, let's calculate this. So 10C4 is 10, 9, 8, 7 divided by 4 factorial is 24. So this is like 8, 3 times 7, 21. So 210. So this is the value of n3. Alright, so the number of ways to form the set S3. Similarly, the last one, n4. Okay, n4 again a combination of 4 letters. Alright, I, J, K, L, M. So we'll have to select 4 letters now. So 4 numbers from the 10 numbers. Alright, 10C4. So we've selected 4. So but this time we have to arrange. So these are just unequal numbers. Alright, no ordering. So we'll have to consider the order also. So once the 4 numbers are selected, so we can arrange them also. In how many ways can you arrange these 4 selected letters? 4 factorial. Alright, so this is the value of n4. But then the question it is asked to find n4 divided by 12. So that is 10C4, which we have already found, 210 multiplied by 4 factorial 24. So divided by, so this 12. So thus that gives you the value 24 by 12, 2. So 420. Alright, so that's all. So that is the answer to the last part of the question. So that means, so we can look at the options, so whichever matches here. The natural numbers A, B and C have LCM and HCF 4020 respectively. The number of ordered triplets A, B, C is. So here 3 numbers are given, A, B and C, whose LCM, the least common multiple, is given to be 4000, and also the highest common factor is given to be 20. Using that, we need to find the total number of possible combinations of values of A, B and C. Alright, so what is given here is the LCM of these numbers A, B and C. So that is given to be 4000. I will write these values in terms of the prime factors, because we are dealing with LCM and HCF. It's important that you get everything in terms of the prime factors. So the 4000 can be written as 2 to the power 5 multiplied by 5 to the power 3. Similarly, so the highest common factor, so the HCF of the numbers is also given. So HCF of A, B, C is given to be 20, which can be written as 2 squared multiplied by 5, or 5 to the power 1. Alright, so these two are given in the question. Now the LCM of these numbers A, B, C is this value. So that means A is a factor of this number and B is also a factor of this number, and so is C. So A, being a factor of that number, will be of the form 2 to the power something multiplied by 5 to the power something. So the only form it can take is 2 to the power some value and 5 to the power some value, because this number cannot have any other prime factor apart from 2 and 5. So this must be 2 to the power something. So I'll take that value x1. Similarly, 5 to the power some value, take it y1. So this x1 can take maximum value 5. So if it exceeds 5, this cannot be the factor of that number. So that means x1 can have maximum value 5. And similarly, the minimum value of x1 is 2, as this number is a factor of this number. The HCF is the common factor. So this number is a factor of this number. So the minimum value of x1 is 2. So x1 can take values from 2 to 5. So the possible values of x1 are 2, 3, 4, 5. So there are 4 possible values of x1 here. And similarly, y1 can take values from 1 to 3. So 1, 2 and 3 are the possible values of y1. Similarly, b is also a factor of this number. So b will also take a similar form. So 2 to the power something, so that can be taken as x2 multiplied by 5 to the power some y2. C is also a factor which can be written as 2 to the power x3 multiplied by 5 to the power y3. So these are the possible values of a, b and c. So the number of ways in which we can assign values for x1, x2 and x3, similarly y1, y2, y3, and that will give you our required answer. See, we know that this x1, x2 and x3, these three values always lie in this range. So the minimum value is 2 and the maximum value is 5. So x1 can take values 2, 3, 4, 5. So there are 4 possible ways in which we can give values to this x1. Similarly, x2 can take 4 possible values and x3 has 4 choices. That means 4 to the power 3 is the number of ways in which we can assign values for x1, x2 and x3. Alright, but that is not the answer, because when you say x1, x2, x3 taking values, 4 possible values, so that may include cases in which this 5 is not included at all. The LCM of these numbers must be 2 to the power 5, which means one of the numbers must be equal to 5. See, if no number is 5, so that means the LCM is not 2 to the power 5. So one number among these three must be equal to 5. Similarly, one number among these three must be equal to 2. Otherwise, this will not be the HCF of the given numbers. So now we subtract the cases in which our condition is not satisfied. So we are going to use the concept of inclusion and exclusion. So subtract the cases in which this 2 is not included in the list. Suppose 2 is removed from the list. Now we are left with 3, 4, 5. Only 3 cases. So x1 can take 3 values. Similarly, x2 can take 3 values. And similarly x3. So 3 to the power 3. So this is the number of cases in which this 2 is not included in that list. Similarly, how many cases are there in which the 5 is not included? So that is also 3 to the power 3 again, because if 5 is not included, 2, 3, 4 are the only choices. So 3 to the power 3. Alright. So this is the number of cases in which one of the number is excluded. Now we have to add the cases in which both the numbers are excluded. So if 2 and 5 are removed from the list, we are just left with 3 and 4. So only 2 choices for each number, 2 to the power 3. Alright.
Why are you adding the last term instead of subtracting?
You are asking me this question like you are hearing about inclusion exclusion for the first time. See, what is the concept of inclusion exclusion? From the total number of cases, you subtract the cases in which our condition is not satisfied. See, we'll have to subtract the cases in which one of our condition is violated, and we add the cases in which 2 conditions are not satisfied, and again subtract the cases in which 3 conditions are not satisfied, and so forth, right? So here the maximum 2 conditions can be violated. So here you see this is the total number of cases and one of the conditions is not satisfied. So either 2 is not included or 5 is not included, plus both the numbers are not included. So that is the basic idea of inclusion exclusion, right? So it's the concept of the union of sets. So this is the required answer. I mean the number of ways to select x1, x2 and x3. So tell me, 64 minus this is 54 plus this is 8. So this gives you the value 18. So 18 is the total number of ways we can choose values for x1, x2 and x3. The same logic applies to the other variable y1, y2 and y3. Alright, so y1, y2 and y3. So these values lie in the interval, okay, 1 to 3. Which means these values can take values 1, 2 or 3. Okay, that means each value y1 has 3 choices, 1, 2 or 3. y2 also has 3 choices. 3 choices, that means 3 to the power 3 is the total number, and similar to this we will subtract the cases in which this 1 is not included. So that means only 2 choices for each element, 2 to the power 3, and similarly if 3 is not included, again 2 to the power 3. Now add the cases in which both the numbers are omitted, so that means only one choice, 2 is the only number left, so only one choice for each number, 1 to the power 3. So if you simplify this, we'll get 27 minus 16 plus 1. So this will be 12. So 12 is the number of ways in which these numbers y1, y2, y3 can be assigned values. Now our required answer must be then, okay, so the number of ways in which this variable can be assigned values, so that is 18, and number of ways in which y1, y2, y3 can be selected is 12. So the total number of ways here is 18 multiplied by 12, okay, total number of combinations. So this value will be equal to 260. So that's it. So that is the answer to the question. If R, S and T are prime numbers and P and Q are positive integers such that the LCM of P and Q is R squared, T to the power 4, S squared, the number of ordered pairs P, Q is. This question is similar to the last question. It's even easier than the last one, as there are only two numbers and only the LCM is given, no HCF given, so there is no lower limit, only 0 is the lower limit. So that means you can just solve this question just following the same steps. So you can do this yourself.
I can do it myself.
Yes, so do this question yourself and just check if you get this answer. Natural numbers x, y and z are factors of the number 2 to the power 4 multiplied by 3 to the power 3, satisfying the condition x, y, z less than or equal to 2 to the power 4 multiplied by 3 to the power 3. The number of ordered triplets x, y, z is. So here in this question, 3 numbers are given x, y and z, which are factors of that number 2 to the power 4 multiplied by 3 cube. If you multiply these 3 numbers x, y and z, we get a value which is less than or equal to that number. Now we'll have to find the total number of combinations of values of x, y and z. So it is given that the product x, y, z is less than or equal to that number 2 to the power 4 multiplied by 3 cube. Alright, and it is given that x, y and z are factors of this number. Like we have seen already, x is a factor of that number, so that must be of the form 2 to the power something multiplied by 3 to the power something, because any factor of this number will be of the same form. So this number, we take x1, so this is y1, so this is x. Similarly, y is also a factor, so which must be of the form, so 2 to the power some number, so call it x2 multiplied by 3 to the power y2. So same goes with z, 2 to the power x3 multiplied by 3 to the power y3. Now if you multiply these 3 numbers, we should get a value which is less than or equal to this. But if you multiply these 3 numbers, the powers get added, x1 plus x2 plus x3, so that must be less than or equal to 4. So x1 plus x2 plus x3, so this value must be less than or equal to 4. Similarly, so y1 plus y2 plus y3, so that must be less than or equal to 3. Alright, so we know how to solve an equation of this type, but this is not an equation, this is an inequality. So for an equation like this, so we know the number of solutions, n plus r minus 1 c r minus 1, but this is an inequality, so we'll convert this into an equation. So this whole value is less than or equal to 4. So x1 plus x2 plus x3 is less than or equal to 4. If this number is less than or equal to 4, if you add some value, and that will become 4. Alright, so if this value is say 3, if you add 1, it will be equal to 4. So whatever this value is, if you add some variable here, so that will be equal to 4, and that value which is added with this, so we can take it as x4. So now it is a question of 4 variable, not 3 variable. So this is an equation now. Now we can use that formula to find the number of solutions. N plus r minus 1 c r minus 1. That means 4 plus 4 minus 1 c 4 minus 1. So this is 7c3. So 7c3 value is 5 times 7, so this is 35. So 35 is the number of ways we can give values to x1, x2, x3. Now similarly, so this equation, so y1 plus y2 plus y3, and we add some value y4 to make it equal to 3. So this is again a similar equation, so use the same formula to find the number of solutions. This is 3 plus 4 minus 1 c 4 minus 1. Okay, so this is 6c3, so this has value 20. So 20 is the number of ways we can give values to y1, y2, y3. So now we want to find the total number of combinations. So our required answer is, the total number of combinations is the product 35 multiplied by 20. So that is 700. So that is the answer to the question. The number of non-negative integral solutions of the equation x1 plus x2 plus x3 equals 20, where x1, x2, x3 less than or equal to 8 is. So here we need to find the number of solutions of equation like x1 plus x2 plus x3 equal to 20. So this is a direct question. So we have a formula for number of solutions of equation like this, n plus r minus 1 c r minus 1. So but here in this question, the upper limit is given. No value should exceed 8, and that makes the question little difficult. Alright, so there are two methods for solving questions of this type when the upper limit is given. When the lower limit is given, there are easier ways to deal with that. But when the upper limit is given, so we can do by these two methods. See, it's given that x1 plus x2 plus x3 equals 20. Now, so we can't use this formula directly, so we'll go back to the basics, right? How we derived this formula using that multinomial expansion. So we are going to use the method directly here. So x1 takes values 0, 1, 2, 3 up to 8. So all the possible values that x1 takes can be written as powers of x, right? So like x to the power 0 plus x to the power 1 plus x square, like this. So the last value is x to the power 8. Okay, now similarly x2 can take value 0, 1, 2, 3 up to 8. So again you write the same expression. Similarly for x3, which means the same expression is written 3 times, so cube. So from this we want the total power 20. So that means coefficient of x to the power 20 is what we need to find from this expression. That is the basic idea of that multinomial application in the equation like this, right? So let us find the coefficient of x to the power 20 from this expression. Alright. So this is like a geometric progression, right? So find the sum of GP, 1 minus x to the power 9 divided by 1 minus x, the whole thing cubed. Alright. So now a minus b cubed, use the formula. So 1 minus 3x to the power 9 plus 3 x to the power 9 squared, so x to the power 18. So that's it. I'm not writing the next term because the next term is x to the power 27. That will not contribute to this x to the power 20 because that power is more than 20 already. So we just want x to the power 20. So that term is not required here. Now 1 minus x to the power 3 minus 3 here. Alright. Now 1 minus 3x to the power 9 plus 3x to the power 18 multiplied by this thing. But this here we need to use the concept of a binomial theorem for rational index, as the power here is a negative number. So what is the formula here? And that is the formula for the coefficient of x to the power n in an expression like this. 1 minus x to the power minus r. From this, if you want to find the coefficient of x to the power n, so the formula here is n plus r minus 1 c r minus 1. See, that is how we got this formula. Alright, so now we are going to use the method directly. So 1 multiplied by, we need x to the power 20 coefficient. Similarly, this x to the power 9 already is there, so we just need x to the power 11 from this. So 3 multiplied by the coefficient of x to the power 11, and also x to the power 18 here, this multiplied by, we just need x to the power 2. So this 1 multiplied by, we need x to the power 20 coefficient. So that is 20 plus 3 minus 1 c 3 minus 1, using that formula. Similarly, minus 3 multiplied by x to the power 9 is there already, we just need x to the power 11. So that is the formula 11 plus 3 minus 1 c 3 minus 1. And similarly, plus 3 multiplied by, so x to the power 18 is there already, we just need x square coefficient, which is 2 plus 3 minus 1 c 3 minus 1. Okay, now if you simplify, you'll get our required answer. So 22 c2 minus 3 multiplied by 11 plus 2, so 13 c2 plus 3 times 4 c2. So this is 22 c2, which is 11 times 21. So 21 multiplied by 11 minus 3 times, so 13 c2 is 6 times 13 plus 3 multiplied by 6. So if you do the simplification, so if you if there is a common factor, we can take it out, like 3. So 3 if you take out, it is 7. 7 times 11, which is 77, minus 6 times 13, which is 78, plus 6. So this gives the value, so minus 1 plus 6, so 5. So 3 times 5, 15. So that's it. So that is the required answer, right? 15 is the number of ways we can find solution to this equation with the given restriction. Now we'll also do this question by another method. Okay, so it is given that an alternative method, x1 plus x2 plus x3 equals 20, but no value should exceed 8. Now let us find total number of solutions, okay, without any restriction, total number of solutions. From that you subtract the cases in which our variables exceed the given value 8. Alright, what is the total number of solutions? So that is 20 plus 3 minus 1 c 3 minus 1. This is the total number of solutions. From this we subtract the cases in which at least one number exceeds our required limit. So we are going to use the concept of inclusion exclusion here. Alright, suppose one number exceeds 8, which means the minimum value of one of the numbers is 9. I'm taking minimum value 9. So x1 is 9. x1 is not exactly equal to 9. I'm assigning x1 minimum value 9, over which if you put more values, it will exceed 9 also. If you put 0, so that will still remain 9, which is more than 8. So minimum value of x1 is taken to be 9. It is like this one. There are 20 identical balls and you put them in 3 distinct boxes. So these 20 identical balls we have to put in 3 boxes, with first box containing minimum 9, which means you take 9 balls from this, you put this 9 balls already in the first box. Now we are just left with 11 boxes, which means our new equation now here is x1 plus x2 plus x3 equals 11. So that equation has number of solutions 11 plus 3 minus 1 c 3 minus 1. So this is the number of solutions in which this value is minimum 9. Okay, now this should be multiplied by 3. So why do you multiply by 3? One of the values exceeds 8. So that value may be x1 or x2 or x3. So either this value is minimum 9 or x2 or x3. So that So 3 cases, so multiply by 3. Alright, now we have to add the cases, right? That is the idea of inclusion exclusion. Add the cases in which two numbers do not satisfy our condition. Two numbers exceed 8, which means not only first number, even the second number is minimum 9, which means you take 9 balls and put it here, 9 balls to put it here, so 18 balls are gone. So remaining, we are left with only 2 balls. So which means our new equation is x1 plus x2 plus x3 equals 2. So what is the number of solutions here? 2 plus 3 minus 1, C3 minus 1, even that one is multiplied by 3, because the numbers which exceed this 8 can be either x1, x2, or x2, x3, or x3, x1. There are 3 cases, or 3C2. So this is the number of cases in which two numbers exceed our limit, the number of cases in which one number exceeds our limit. This is the total. So if we subtract, we'll get our required answer. Now, is it possible that all the 3 numbers exceed our required limit? So that is not possible. If you put 9, 9, 9 here, so that will exceed 20, right? 27, that is more than 20. So at the most 2 numbers can exceed our limit. So that we have already taken into account. So now let us do the calculation here. So this value is 22 C2 minus, this is 11 plus 2, which is 13 C2 multiplied by 3 plus 4 C2 times 3. So if you do this calculation, so if you observe that expression is also same as this expression only, 22 C2 minus, so the same expression, so basically the answer will be same. So this answer will be 15 then. Alright, so that is the answer to the question. So this type of question, when the upper limit is given, you can either use this method of the multinomial application here, or we can use the inclusion exclusion idea. Alright, so 15 is the answer to the question. An engineer is required to visit a factory for exactly 4 days during the first 15 days of every month, and it is mandatory that no 2 visits take place on consecutive days. Then the number of all possible ways in which such visits to the factory can be made by the engineer during 1 to 15 June 2021 is. So here, an engineer has to visit a factory on 4 days out of the first 15 days, but he can't visit on 2 consecutive days. He has to leave gaps between the days, right? So this is a standard question usually done as part of the course. Now you see, this is an example. Our Chintu is the engineer here. He has to visit on any 4 days out of the 15 days. So initially he is on the 4th day. So that means he has not visited on the first 3 days. So this gap is counted as x1. So x1 is the number of days on which he has not visited the place initially. So that x1 is 3 for this example. And now he is on the 4th day. Now he can't jump to the next one, so he has to leave some gap, and that gap is counted as x2. Similarly, the next gap is counted as x3, x4, x5. So these are the gaps. So if you add all these values, x1 plus x2 plus x3 plus x4 plus x5, and that should be equal to the total 15 minus 4. On 4 days he has visited. That means on the remaining 15 minus 4, 11 days he has not visited the place. So these values add up to 11. So that total x1 plus x2 plus x3 plus x4 plus x5. So this total must be equal to 11. So the number of solutions of this equation will give you our required answer. But there are restrictions on these variables. This x2 should be minimum 1. It cannot be 0. If x2 is 0, which means he has visited the place on consecutive days, so no gap. So x3 should also be minimum 1, and same goes with x4. Now x1 can be 0. If x1 is 0, he has visited the place on the first day itself. Similarly, x5 can be 0. So that means he has visited on the last day. So x1, x5 can be 0, but these values should be minimum 1. So we know how to deal with this type of question. Minimum value is known. So 1 is the minimum value. So you put 1 here, so 1 here, so 1 here already, right? So that means the minimum value is assigned to this, which means our new equation will have, instead of 11, so 11 minus 3, that is 8. So now our new equation here is x1 plus x2 plus x3 plus x4 plus x5 equals 8 after assigning values to the 3 variables. Okay, now what is the formula for the number of solutions? 8 plus 5 minus 1 C 5 minus 1. So this is the number of solutions, right? N plus R minus 1 C R minus 1. So this will give you our required answer. So this value is 12 C4. So if you do the calculation here, 12, 11, 10 multiplied by 9 divided by 4 factorial is 24. So if you simplify, so this is 2, so 11, so 990 divided by 2, so that is 495. So that's it. So that is the answer to the question, right? In a hotel, 4 rooms are available. 6 persons are to be accommodated in these 4 rooms in such a way that each of these rooms contains at least 1 person and at most 2 persons. Then the number of all such possible ways in which this can be done is. So here there are 6 people to be accommodated in 4 rooms. So obviously some of these rooms should contain more than one person, right? And each room should contain minimum one person. Suppose these 4 people get into the 4 rooms, okay, and we are still left with 2 more people, and they should take some of these rooms only, but they both cannot get into the same room because the maximum capacity is given to be 2. So they should take different rooms. So this is one example. Alright, so there are 6 people, so they can take these 4 rooms. If you take this example, the first room contains 2 people and the next room 1, 1 and 2. This is one example. Is there any other way we can distribute? So this is the only way. The other things are just arrangements, right? Instead of 2, 1, 1, 2, it can be arranged like 2, 2, 1, 1 or 2, 1, 2, 1. So there are many possible arrangements, but this is fixed that 2 of these rooms should contain 2 people and the other 2 should contain just 1 person each. So this is the only possible distribution. So this is simple idea of groups. So tell me, what is the formula for the number of ways we can distribute this object into groups? See, 6 factorial divided by 2 factorial, 1 factorial, 1 factorial, 2 factorial. So this is the number of ways we can form groups out of these 6 people. But here, so this can be arranged also. It can be instead of 1, 2, 1, 1, 2, it can be 2, 2, 1, 1, 1, 1, 2, 2. So what are the number of possible arrangements here? So 4 objects, so that can be arranged in 4 factorial divided by, so there are identical objects, these 2 are identical, so divide by 2 factorial. Another set of identical objects, again divide by 2 factorial. Alright, so this is the number of ways this can be done. So if you do the simplification, so this is 720 divided by 2, 2, 2, 8 multiplied by 4 factorial is 24. Okay, there is another 2. 720 divided by 8, so 90 multiplied by, okay, 12. So that gives you the answer 1080. So that's it. So this is the number of ways this can be done. Alright, so that is the answer to the question.
JE advanced questions of this chapter seem to be very simple.
Usually the questions of this chapter that appear in the exam are very simple, but sometimes the questions do get tricky, like in this example. Let n1 less than n2 less than n3 less than n4 less than n5 be positive integers such that n1 plus n2 plus n3 plus n4 plus n5 equals 20. Then the number of such distinct arrangements is. See, this question does not involve any concept of permutation and combination as such, so that makes this question a little difficult or easier, it depends. So there are 5 variables given, n1, n2, n3, n4, n5. They'll always follow this order. Okay, n1 is the least and the next n2, etc. Alright, now we need to find the number of solutions of this equation. So it is given that n1 plus n2 plus n3 plus n4 plus n5. So that value is given to be 20. Okay, right now we need to find the number of solutions. If it is simply number of solutions, we can use the formula also, but there are restrictions here. n1 is the least and n2 is bigger than n1 and many more conditions. Okay, now because n2 is bigger than n1, I will take it this way, n1 plus n2 is bigger than n1, so that can be written as n1 plus something. I'll take that something as x1. So this is one way to do this question. This is not a unique way to do it because it is not very conceptual. So it's simple counting, so you can do it whichever way you want. So n2 is bigger than n1, so I'm taking that n2 as n1 plus something. Okay, so x1. And n3 is bigger than n1, I mean n2. So this value will be bigger than this one, which means this n3 can be written as n1 plus x1 plus another value x2. Alright, and similarly n4 is bigger than n3, so that will be n1 plus x1 plus x2 plus another value x3 plus, and n5 is bigger than this value, so we'll take it as n1 plus x1 plus x2 plus x3 plus x4. So this total is 20. Okay, now if you simplify, n1 appears 5 times, so this is 5 times n1 plus 4x1 plus 3x2 plus 2x3 plus x4, that equals 20. Okay, right, so this is our new equation. Now this n1, x1, all these values are bigger than 0, right? So no value is 0, minimum 1. So that means we will assign values, minimum value 1 for each variable. Alright, so 1, that is the usual method, right? So if the minimum value is given, you assign that value to each variable. So 1 here and similarly 1. So each variable is assigned a minimum value 1, so which means, so this total becomes 5 plus 4 plus 3 plus 2 plus 1, so that is 15. So instead of 20 we will get 5 only. 20 minus 15, that is 5. So our new equation is 5n1 plus 4x1 plus 3x2 plus 2x3 plus x4, so that equals simply 5. Okay, I'm using the same variable n1 here, since if you want you can take another new variable here. So here n1 should be minimum 1, but here n1 can be 0 also, because we have already assigned 1 to each variable, so each value here can be 0 also. Alright, now we just have to count. Alright, what are the possible ways we can get this 5? So what are the different ways we can get 5? So 5 plus all values are 0, so that is 5, so which means I'm choosing n1 as 1. So n1 is 1 time 5, so that is 5 plus the remaining values are 0, 0, 0, 0, 0. So this is one way to get 5. Okay, now is there any other way to get 5? So 5 plus 0 is 5, and 4 plus 1. Okay, 4 plus 1 is also 5, which means the other variable should be taken as 0. So 0, so 4 times 1, and these values are 0, and this x4 can be taken as 1. So 4 plus 1, that is 5. And any other way we can get 5? 3 plus 2 is 5. So you take x2 as 1 and x3 1. So 3 plus 2 is 5. The other variables will be 0. So 0, 0, and this is 1. This is also 1. So 3 plus 2, and that is equal to 5. Alright. And what other ways we can get 5? So 2 we can take 2 times. Alright. So 2 we can take 2 times, which means 4 plus 1. So 0, 0, 0. So x3 you take 2. And x4 you take 1, which means 2 times 2, which is 4, 4 plus 1, 5. Okay, and so take this value 0, and 3 you take x2 1, so 3 plus 2, take x4 as 2, which means 3 plus 2, so that is also 5. So 1, take this value 0, so 3 times 1, that is 3, plus here 2, so 3 plus 2 is 5. Okay, and we can take x4. So take this value is 0, alright, and take 2 times. Okay, so that we have already taken. So take 2 1 time. Alright, 2 times 1, so that is 2, and take x4 3, which means 2 times 1 is 2 plus 3, so that is 5. And is there any other way? We can take all the values. So 0, 0, 0, 0. Here x4 is 5. Okay, so 5 plus all the values are 0, so this is also 5. So these are the different ways to get the answer. So if you count the number of solutions, so we get the answer 7. So there are 7 possible ways we can find solution to this equation. Alright, so that is the answer to the question. Alright, see, the problem with this type of question is that this does not involve any concept, simple counting. So if you have a bad day, you might miss 1 or 2 solutions and your whole effort goes in vain, but conceptually it's a very simple question. 10 distinct balls are to be placed in 4 boxes numbered 1, 2, 3 and 4, such that the even numbered box should contain even number of balls. The number of ways in which this can be done is. So here we have 10 distinct balls which are to be placed in 4 distinct boxes, and also some extra condition is given. The even numbered box should contain only even number of objects. So if this condition was not there, we could have done it directly. So the first ball can be placed in 4 ways, any one of the 4 boxes. Second ball can be done in 4 ways, and similarly the 10th ball can be done in 4 ways. So that means 4 to the power 10, that would be the answer. But there is an extra condition here. The even numbered box should contain only even number of objects. So this extra condition makes this question a little difficult. See, so we have to go back to the basic method of finding the number of solutions of the equation, right? N plus r minus 1 c r minus 1. So we use that the multinomial expansion and stuff like that. Alright, so we have to use that idea. See, the first box contains x1 objects, second box contains x2 objects, third x3, fourth x4. So this total must be equal to 10. Alright, because totally we have 10 balls. But the solution of this is not our answer, because the balls here are not identical, distinct. It not only matters how many balls are put in each box, but which ball, that also matters. But at least first of all we take care of the number of balls in each box. So this x2 should be even number. So this x2 must be an even number, something like 2m, and x4 is also an even number, say 2m. So these two values are even and no restriction on x1 and x3. So we use the basic method here. So what are the possible values x1 can take? 0, 1, 2, 3, etc. up to 10. So that you write as power of x. So x to the power 0 plus x to the power 1 plus x squared, etc. up to x to the power 10. So all these power 0, 1, 2, 3 are the possible values of x1. Similarly, x2. But x2 can take only even number, so all the power should be even. X to the power 0, x squared, etc. up to x to the power 10. Alright, similarly the next one, x3 can take any value 0, 1, 2, 3, etc. But that is same as this term will be written again. So we can write it as a square. So this term is repeated 2 times. So here similarly x4 will have only even numbers, so that means the same term is repeated, so this square. From this we need to find the total 10, which means the coefficient of x to the power 10 is what we need to find. So the coefficient of x to the power 10, so that will give you our required answer. But here the balls are distinct, not identical. If the balls are identical, then this will give you the direct answer. Coefficient of x to the power 10 in this expansion, that will give you our required answer. But we have not taken care of that aspect. The balls are distinct here. So suppose this has some 5 balls and this has 3 balls. So 2 balls, 0 balls. And it also matters which 5 balls are placed in the first box. Not only how many balls, which 5 balls or which 3 balls. So which means we have to arrange these 10 balls also. So these 10 balls can be arranged in 10 factorial ways. Do you understand? Suppose 5 balls are placed here, 4 balls here. So we can arrange this 10 balls. So 10 factorial ways we can arrange them. Okay. But there is a problem again. If 5 balls are put in the first box, these 5 balls are not going to be arranged. Overall there is an arrangement. So these 5 balls here or here, it matters. But within the box, the balls are not to be arranged, right? But 10 factorial arranges everything. So, but within the box, it doesn't matter which one is the first one, second one. So if suppose here, the first box contains 1 ball. Here the first box contains 2 balls. So when the first box contains 2 balls, within that there is no arrangement. So what we have to do is, you have to divide this by 2 factorial. It is just like the identical objects, right? Because within the box, so we can consider them to be identical. So 2 factorial you have to divide. And here 1, so divide by 1 factorial. Here 10 balls are there, you have to divide by 10 factorial. Because within the box there is no arrangement, but overall there is an arrangement 10 factorial. So same here, so divide by 2 factorial. So here 10 factorial. So this is no more a geometric progression. So this looks like an exponential series, right? 1 plus x by 1 factorial plus x squared by 2 factorial, etc. So this is an exponential series. But exponential series is not finite, it is infinite series. There are other terms. Next term like x to the power 11 divided by 11 factorial, it goes till infinity. But can we treat this to be exponential series? But even if there are extra terms, will it affect our answer? Because our maximum power is 10. Even if it has extra term like x to the power 11 divided by 11 factorial, 12, 13, any number of terms other than this, okay, that will not affect our answer. So we can still consider this to be an exponential series, because that is not going to affect our answer. So this is exponential series squared. And here also exponential series, but only even powers are there. So what is the formula for the exponential series of only even power? So e to the power x, e to the minus x divided by 2 squared. So this is the exponential series with only even powers. That's all. Let us do the simplification. So this is 10 factorial and e to the power 2x, and this one is e to the power 2x plus 2 plus e to the power minus 2x divided by 4. Alright, so if you simplify this, this is 10 factorial divided by 4, and if you multiply inside, so it is e to the power 4x plus 2 e to the power 2x plus 1. Okay, now simplify this. This is 10 factorial divided by, so we need the coefficient of x to the power 10 in this. So that is the standard expression, right? What is the coefficient of x to the power 10 in e to the power 4x? That is 4 raised to the power 10 divided by 10 factorial plus 2. Similarly, e to the power 2x, the coefficient of x to the power 10 is 2 to the power 10 divided by 10 factorial. Alright, if we do the multiplication here, so 10 factorial gets cancelled, 1 4 gets cancelled, so it is 4 to the power 9. Okay, and 1 2 cancelled, so it is 2 to the power 9. Alright, so that is the answer to the question. There are 10 true or false questions with marks 4, -1 or 0. The number of ways in which a student can get 1 mark is. So here in this question, 10 true or false questions are there with marks 4, 0 and -1. It is understood, right? 4 marks for the correct answer and -1 for the wrong answer, and 0 if it is unattempted. So this mark distribution is there. In how many different ways you can get 1 mark? That's what we're going to calculate, right? Yes. Suppose in the first question he got x1 marks. In the second question he got x2 marks. So in the third question he got x3 marks. So like that, in the 10th question he got x10 marks, but that total should be 1. Totally he got 1 marks, but in each question how many marks he got, so that is a variable. So, but this is not the number of solutions of this equation, because there are a lot of restrictions. This x1 can take values 4, 0, -1. These are the only possible values of x1. Similarly x2, x3 and the other variables. So now we are going to use the concept of that multinomial expansion. So x1 takes values 4, 0 and 1, which we will write as the powers of x. So x to the power 4 plus x to the power 0 plus x to the power minus 1. So these powers are the possible values of this variable x1. Alright. Similarly for x2, same expression. So this whole number to the power 10. Because for all the variables, so the possible values are 4, 0 and minus 1. So to the power 10. From this we want to find the total value 1, which means coefficient of x to the power 1 in this expansion. That is what our answer is, right? So now let us find the coefficient of x to the power 1 from this expansion. Okay, this is a random term, right? This doesn't have any pattern, so we'll have to simplify this. So this is x to the power minus 1, so 1 divided by x. So if you simplify that, you'll get, so coefficient of x to the power 1 in this, if you do, we'll get x to the power 5 plus x plus 1 to the power 10 divided by, so x to the power 10. Alright, so if you simplify this, you get this. Alright, so from this we want x coefficient. So already there is x to the power 10 in the denominator. So from the numerator, what we want is the coefficient of x to the power 11, right? If x to the power 11 divided by x to the power 10, that will give you x. So that means what we want from the numerator is the coefficient of x to the power 11. So the question reduces to finding coefficient of x to the power 11 from this expansion, x to the power 5 plus x plus 1 to the power 10. Okay, now here three terms are there. It's not binomial expansion, so we'll have to use the concept of multinomial expansion. Alright, so what is the formula for the multinomial expansion? So the power is 10 here, so that means this is 10 factorial divided by some p factorial, q factorial, r factorial, and this number to the power p, which means x to the power 5, the whole thing to the power p, and similarly the second variable x to the power q, and similarly 1 to the power this r. Okay, so if you simplify, so we'll get 10 factorial divided by p factorial, q factorial, r factorial, and x to the power 5p plus q. Alright, so this is the power of x here, 5p plus q, but we want x to the power 11, which means this number 5p plus q must be equal to 11. So 5p plus q must be equal to 11. And already there is a condition, this p plus q plus r must be equal to the total value 10. So p plus q plus r, that equals 10. So now we'll have to find the number of possible combinations of values of p, q and r. So let us write all possible values of p, q and r. Same, 5p plus q is 11. Let me take the smallest possible value. Suppose p is 0, then q must be 11, so that is not possible. So maximum value is 10 only. So let us take the minimum value of p to be 1. So suppose p is 1, then q must be equal to 6. And the total value is 10, so that means r is 3. Okay, so this is one possibility. Similarly, let us take p value next 2. So then q will be 1. So p is 2, q is 1. In that case, r is 7. That's all. These are the only possibilities, because if you take the next value p3, so that will exceed our limit. So these are the only possible combinations. So let us take the first combination 1, 6, 3. That will give you one coefficient. So that value is 10 factorial divided by 1 factorial, 6 factorial, 3 factorial, and similarly the next term plus 10 factorial divided by 2 factorial, 1 factorial, 7 factorial. So let's simplify this. So this is 10 factorial divided by, so let us take some common values. So 10 factorial I'm taking out, divided by, so let us take out 7 factorial and then 3 factorial. So if you take this value out, so this will become 7 plus, so 3 factorial is taken out, so this is 3. Okay, so this is 10 factorial divided by 7 factorial. So that can be written as 10, 9, 8 divided by 3 factorial is 6 multiplied by 10 again. Alright, so this will give you the value 4 multiplied by 3, 12. So this is the answer, 1200. So that is the answer to the question. Alright, so we make use of this multinomial expansion to get the answer to the question. Now we'll also do this question by another method. So alternative method. Alright, see, suppose, so these are the possible marks, right? Either 4 marks or -1 or 0. So these are the possible marks, right? In how many questions he got 4 marks, which means how many questions he got right? Suppose 1 question. So he got 4 marks. That means the total must be 1. That means he got the remaining 3 questions wrong. So 3 questions minus 1, that makes the total 1. So the 6th question unattempted. Alright, so is there any other combination here? So 2 questions he got right, which means 8 marks. That means 7 questions wrong. So 7 times minus 1, that is minus 7. 8 minus 7, that is 1. And the remaining 1 question, 0 marks. Alright, okay, so that's all. These are the possible combinations. Alright, now we will select. He got 1 question right. That means out of the 10 questions, any 1 question can be right. Let us select that. So from the 10 question, you select 1 question which is right. Alright, multiplied by, from the remaining 9 questions, 3 questions are wrong. Which 3 questions? You can select it. So 9C3. Alright, this is the first possible value. The remaining automatically 6 questions, so they are unattempted. Plus, now 2 questions right in the second case. So which 2 questions? Selected. So 10C2 times, from the remaining 8 questions, we have to select 7 questions. So 8C7. So let us do this calculation here. So 10 factorial divided by 9 factorial, 1 factorial. This is 9 factorial by 6 factorial, 3 factorial. This is 10 factorial by 8 factorial, 2 factorial. So this is 8 factorial divided by 1 factorial, 7 factorial. Alright, so some terms get cancelled. This 9 factorial gets cancelled and 8 factorial here. So if you observe, it is the same expression here, right? 10 factorial divided by 6 factorial, 3 factorial. Similarly, 10 factorial divided by 2 factorial, 7 factorial. That means the answer must be same, right? So this answer here is also this 1200. Alright, this combination, right? These 2 combinations are same here also, right? But we arrived at this combination by doing all the multinomial expansion. But here we have directly guessed it, right? So this is just another way to do it. But learn this method also, right? This may be required for some type of questions. So these are the 2 methods by which we can solve this question. Okay. Seven letters are to be placed in 7 addressed envelopes such that no letter is placed in the correct envelope. If letters 1 and 3 are always placed in envelopes 2 and 4 respectively, then the number of ways in which this can be done is. So this is a standard derangement question, right? Letters are placed in the envelope with no letter matching the correct envelope. So this is the formula for derangement. So this is the number of ways in which we can place n letters in n envelopes with no letter matching the correct envelope. Alright, so this formula cannot be used here directly as there are some extra conditions given in the question. The letter 1 is always placed in envelope 2 and letter 3 is always placed in envelope 4. With these conditions, how many possible combinations are there? So that's what we have to find. But the letter 1 is always placed in envelope 2. So that means we have no role to play, already done. So that means you keep it aside. Similarly, so letter 3 is always placed in envelope 4, so that also is kept aside. So the remaining 5 letters we have to mess up. Alright, so let us find the derangement of 5 objects. So derangement of the remaining 5 letters. So how many ways we can place these 5 letters in the 5 envelopes with nothing matching? So that is the derangement of 5. So let us denote this by d5, which is 5 factorial multiplied by 1 minus 1 by 1 factorial plus etc. up to 5 factorial. Alright, so this if you calculate, it will come out to be 44. So it is better if you remember these values. So derangement of 5 objects, so that is 44. Alright, if you don't remember, so we'll have to do this calculation. Alright, anyway, this calculation can be done, so I've written the value directly. Alright, but that is not the answer to the question, because when you consider this derangement of the remaining 5 objects, so here the letter 2 corresponds to the envelope 1, but we have considered the cases in which the letter 2 is not placed in envelope 1. But that is possible here, right? Letter 2 can be placed in envelope 1, but we have eliminated that case. Similarly, the letter 4 here is not placed in envelope 3, but that case should be counted. So we have not counted those cases, we have eliminated all those cases, which means we will have to add these cases separately. So this derangement eliminates all those possibilities also. So let us count them separately. So let us take the cases in which the letter 2 is placed in envelope 1. So which means we have only the remaining 4 letters. So this is the derangement of 4 letters. So d4, so that is equal to 4 factorial multiplied by 1 minus 1 by 1 factorial, etc. Alright, so this is 4 factorial. So that value is 9. Okay, similarly, so the letter 4 can be placed in envelope 3. So that means that case should also be considered. Letter 4 is placed in envelope 3. So that is again d4, because the remaining 4 letters, so d4, so that equals the same formula, 4 factorial, 1 minus 1 by 1 factorial, etc. 1 by 4 factorial. So that is again 9. And it is also possible that both these cases happen simultaneously, which means letter 2 is placed in E1, letter 4 is placed in E3. So both these cases together, so L2 is placed in E1 and L4 is placed in E3. Okay, both the cases together. So that is D3, because remaining we have 3 letters, so D3. So D3 equals so 3 factorial multiplied by 1 minus 1 by 1 factorial last 1 by 3 factorial. This value is 2. So this total will give you our required answer, right? 44 plus 9 plus 9 plus 2 is 20 plus 44. So 64 is the required answer, right?
Are there no repetitions?
See, there are no repetitions here. See, when you consider the case when L2 is placed in E1, so we consider the derangement of the remaining 4 objects. That means, so that rules out the case when L4 is placed in E3. Alright, so this has to be added separately. And similarly, when L4 is placed in E3, so we have deranged the remaining cases. So that means, so these two cases have nothing in common. So they have to be added separately. It is not like inclusion, exclusion, right? So here, there are no common values, and so this has to be added separately. Alright, so all these cases are exclusive. Alright, so that's why we consider all these cases separately, and this total is what our answer is, right? 6 cards in 6 envelopes are numbered 1, 2, 3, 4, 5, 6, and cards are to be placed in envelopes so that each envelope contains exactly 1 card and no card is placed in the envelope bearing the same number. And moreover, the card numbered 1 is always placed in envelope 2, then the number of ways it can be done is. See, this question is similar to the last question, right? The same concept of derangement, and unlike the last question, instead of 2 conditions, just 1 condition is given, so that makes the question even easier. So you can complete this yourself, and this is the answer to the question. Are you ready for a few more questions?
No. I'm beat.
So let's call it a day then, shall we?